So our last presenter in this session is Erwin Glogan, who is a full professor at INRS in Quebec City. He holds the Canada Chair in Geophysical Data Assimilation for 3D stochastic geological modeling. Short and sweet.
So I'll be the one representing the dark side today. I will talk about machine learning and try maybe to make it clear what is machine learning. And just to start, for those who did geophysical inversion or any kind of optimization, machine learning is just a type of inversion. And also, we just to explain where I come from, I'm from INRS, so we are a very small institute in Quebec City, but quite active in the field of machine learning. 2 companies or startups were built or were founded from my former students. So the second place at the Integra Gold Rush Challenge, so they won, but we like them. And a new company, GeoLearn, who specialize in machine learning for any kind of geoscientific applications. Of course, we have a lot of partners, and I would like to particularly thank Mira Geoscience for the support, for any kind of support, data, software, and the team members of INRS. I won't cite them here, you can read. So I have one single question that I want to raise for that presentation is, can we predict lithology and or grades combining borehole and or surface geophysical data, geochemical data, and geological data? So we'll see how can we answer to that questions. So obviously, the way we see machine learning or optimization is to build tools for geologists and mining engineers. We don't want to replace geologists. I mean, we cannot replace geologists, unfortunately. There are some hypotheses that we have to pose. First, geophysical measurements never lie. It's a measurement. Processing does. Inversion, for example, is a killer for further quantitative views of geophysical data because most inversion codes are designed under least square hypothesis. So it's good to infer the mean, but it fails to infer the lower and upper tail of your distribution. Also, one of the claim that we make as a data scientist, we need data. We need more data. We need more collocated data. And from the very beginning of a mine project. And that's also posed some questions about databases. I think one of the things that almost no people care about is the basis and the standard or data format. It's very important from the beginning to have format, and we should, as geoscientists, sit together and decide what format should have the data. The method that we propose is basically very simple, as you all do, is to assimilate in time and space geophysical, geochemical, and geological data, and geological and geophysical models also. How can we include those information into our predictions? And the gain, I mean, just to say the gain is to have a better understanding and better exploitation of the mines. So one of the game changer is to acquire collocated data, as I said, and I just make some advertisement for one of my colleagues that built this nice laboratory, mobile laboratory at INRS. It has a multi-sensor co-logger, non-destructive measurements on core, and it can go on the mine site, so it's very, very efficient. You can see inside the lab, so there is density, gamma, mineralogy, spectrophotometry, magnetic susceptibility, XRF, and photographs also, and it can be improved. And but this is the game changer, because now you can have collocated data, geophysical, geochemical, and geological data, and then you can do statistics. And as Professor West just raised, machine learning is just a tool that does inversion. And these tools are very dangerous because basically they want to skip the forward modeling and forward inversion or inverse modeling. So you need a lot of data and a lot of periodicity. And the term was exactly right. You need a lot of samples exactly the same that repeat a lot of time, then your machine can learn from that experiment. But the type of data that you can get from those multi-sensor core logger are shown on that slide. So you have density, susceptibility, reflectivity, and different mineralogy. And of course, it's very, very difficult to interpret all those data together, because usually we're good to interpret 2 data together, maybe 3, and then it's not possible. So the question now is, how can we combine all those data together? And those data are also generated now in time. So we have a lot of data that are acquired every day, and you want to crunch it every day, or to process them every day. One of the problem also that you're facing is these data are not a property of interest. We measure easily the density, the conductivity, and different type of physical or chemical variables, but you cannot directly infer the data that you really look for, the grades, the lithology. And there is no common model to directly switch from all those data jointly and inverse your lithology. So that's where machine learning can play a very interesting role. And one other thing also we really like to do is how to include qualitative data, such as the geological model. Most of the time, the geologists know very well what's in the ground. They don't know exactly where, but they know at least the type of geological scenarios. And the same for the geophysical models. You know, when the companies send you inverse conductivity 3D field, these are no data, these are models. So how to include those models in the combined integration. So a lot of people talk nowadays about machine learning or artificial intelligence. We all hear about IBM Watson algorithms. And these are very powerful tools, but unfortunately, most of them are not applicable in geosciences. Because basically, as geophysicists or geoscientists, we look for anomalies. So basically, we look for non-periodic anomalies. This is one anomaly among vast continuous rocks that has no interesting data for us. So the way we approach machine learning is we have on the left the classical machine learning processing. So you have big data, a lot of data, all kind of data. You go to machine learning, then you wait some kind of time, push some buttons, and then you have your prediction, and you can do exploration vectors or any kind of stuff. This is not possible. Unfortunately, again, you need to talk to your geologist. Geological knowledge is very important. In geosciences, in AI, we talk about feature engineering and how to process the data to make them more efficient and more informative about what you're looking for is very, very, very important. And you cannot skip the geological knowledge at all. I just explained, oh, there is an interesting mistake in the, just to explain quickly what is supervised machine learning or any kind of AI that are very interesting for us. Basically, you try to find a function that defines a rock type. Here, a limestone, sandstone, and obsidian. You need to define a specific function for each type of rock. How to do that? So you need a lot of samples of images of rocks. Then you try to extract the more characteristic feature of an image. That's what we call feature engineering. Then you extract some training set, so you extract some rocks, and build or calibrate a model. In geophysics, we're used to do that, but the only difference is we have the physics behind. The function is the physics that links, for example, the measured potential at the surface and the conductivity in the ground. Here, we skip that model by assuming that our samples is representative of all the ground, and we have enough information to define the ground only on characteristics of an image or a process. Then, when you have your model calibrated, you can test your algorithm. So here you have an image, extract these features, and do the predictions. So this is as simple as it. And as also many people say, you have multiple free softwares that can do nice AI prediction for you. The simplest are regressions. You have distances like k-means or clustering. You have, and obviously, you need more and more information when you go from the left to the right and also top to bottom. So if you want to do neural network and deep learning, you need a lot of data and a lot of stationary data. So the process that you're studying reproduce a lot. And people were talking before about images recognition that works very well to recognize dogs from cats. That's true. But if you have a Dalmatian, you know, those white dogs with black patches, if the Dalmatian is totally black with only white patches, it's still a Dalmatian, and no algorithm can recognize it. So there is a lot of work, I think, before using neural networks in geosciences and in mineral exploration. But still, there is some hope. You have the Bayesian probability or the Bayesian algorithms. We all know Bayesian statistics because we do inversion. But the new algorithm that works pretty well in our case are the ensemble methods, some kind of decision trees, smart decision trees. And one of the statement also I want to stress here, those algorithms are free, but not anyone should be allowed to use it. You have to be an expert and play a lot with those softwares to be sure that what you do is coherent. As part of this community, we really push to free software. So we have all our codes available on GitHub. And so please go on our website and get the codes and play with it. Now I will go through examples. The first one was to develop a tool to revisit your assays. We tested our methodology at the VMS gold deposit at Lalor, Manitoba. The job was done by Antoine Caté and Lorenzo Perazzi and I. So very quickly, the main idea is to build a learning machine model to predict gold from multiple geophysical logs. So a nice image from the VMS deposit at Lalor. So we have the assays, classic, very conventional ones. And here are the geophysical logs acquired by DJI. And this is very difficult for a human brain to process all those data together. There are too many variables. They are too complex. We are good to interpret correlation. So you do a cross plot, your conductivity against your grade, and you can try to find trends on that cross plot. But then if you have multiple variables, and when the texture of the response is more informative than the correlation, then it's quite a challenge to interpret all those data together. And also, if you decided to do by your own, it's user dependent. If another geologist, another geophysicist will come later and have a totally different interpretation. So we used ensemble methods, and the one we choose on that case is the random forest. Random forest is known to won almost all the hackathons in geosciences for the last 5 years. That's what people at SGS used, I think, and also gradient boosting. Also, I just wanted to stress again, why not DNN? We're not deep enough. We don't have enough data. There is not enough replicability in our data. So we need to have, to adapt existing algorithms for our own purposes. And one of the good things about ensemble methods, it's not black box. well, we'll say gray box. I like the term gray box. It's not that black, not even transparent. But at least you can have some kind of ranking of the features that are more informative on the goal or the task you want to achieve. So in that case, for example, to classify or to estimate the probability of the goal to be above a given threshold or a given cutoff, the most informative variable is the maximum of the neutron measurements. So you have all the data or the variable that are being extracted and ranked. And one also other conclusion that we can get from those experiments is we cannot simplify. There is no point on looking for the 3, 4, or 5, 10 variables that are the most informative. Those algorithms are able to tackle 100 variables at a time. And if they say that the 99 is carry 1% of the response, why throw it away? So the important is to look at the data, look at the ranking. If the ranking has no sense at all, then you can question your algorithms or the feature engineering that you have done previously. But don't throw away the data. One of the things also we recommend, those algorithms are free, so test all of them, the one you can, because it's not true that the best algorithm at what point will be the same or will be the winner after 5, 6, 7, 8 years of your mining exploitation. So in that case, also one of the statements that we can pose is there is no such difference between the algorithms. You can have some maybe 10, 20% more accuracy, but that's not that important. The most important is the work you've done before by doing feature engineering on your data. So you have to work your data before. So some results here on the left, you have the assays. On the right, you have the probability of being above a given threshold. And on the right, you have the classification based on the training images, on the AI classification, sorry. So it's not that bad, I mean, quite good. One of the things also we figured out that was interesting is even the area that were not assays or no geochemical analysis were done, it seems that there is some kind of response on the geophysical data. So I think it's nice to revisit your assays and say, okay, maybe we should do some geochemical analysis at that specific part of my well or hole. Another example is core image classification as a tool for geologists to help his task when logging. So the idea is very simple. You have a core sample on the left. You can acquire a lot of pictures on that core, and then do a classification based on the photographs. So here is an example of photograph or core image on one of the example that we show. In that case, we have about 9 kilometers of core photographs. And we have also a classification made by geologists. So we were able to test in our function. Basically here, what we did is we extract some features on the image. I mean, it looks like an image, but it's alpha cylinder. We have to also take that into account for the texture analysis. But we extract a lot of features on those images, and we did a classification. So on the left, you have the logs done by the geologist, and on the right, you have the predicted logs made by the machine after learning. So we have 90% of accuracy, and it took less than 10 minutes on laptop to do the full logging. And for us, we see that as a really nice tool for geologists to revisit their logs, or even you can imagine that the core are extracted and the photographs are taken in real time. And when he starts his own logging, he has a pseudo log on his laptop or on his portable device. So I think he can help the geologist. Then I switched to another type of data assimilation based on Bayesian formulation. the idea here is we all know that conventional least square inversion fails to further quantitative applications. So we built a Bayesian framework to assimilate surface and borehole geophysical data to generate high-resolution density and electoral conductivity models. So basically, here what we start with is the geological model. So on the left, I don't know if there is no pointer on that. No. Oh. Can I go back? There is no light. So on the left, you have the geological model. So the geologists of the mine built a model. And we use known geostatistical tools to generate multiple equivalent or equiprobable scenarios of the geology. And then all those models have to be populated by density, resistivity, and grade data. So we used conventional co-simulation or Bayesian simulation data to populate the model on the right. So there are the models on the far right. We only show the slices to be more visible. And all those models now can be served as a model or mock-up of our deposit. So we can do forward modeling, any kind of forward modeling, gravity, the electrical conductivity, any data that you have. And you can compare the forward model geophysical data directly with the raw geophysical information or data. So there is no inversion at all. So if the model, the geological model at the beginning is good, then you end up with the scenarios that can be also validated by your geophysical data. And if it's not validated by your geophysical data, then you have to sit with your geologist, say, okay, it doesn't fit, but at least you have one platform to talk together. And this is also one of the outcomes of what John McGaughey called the Common Earth model. I think it's one of the tools that we also should focus on for the next year. How to combine our information in one single database that we can visit together. The last example, I'm late on the schedule. It's an old project that we also had started with, I think, Alan King at that time. It was a nickel grade estimation at Voisey's Bay using crosswave seismic tomography. So the idea is very simple. Once again, we cannot do a conventional least square inversion because it fails to estimate the low and upper tail of the distribution. So at that time, we decided to build a new Bayesian formulation for doing the inversion. So here are the data. So this is one inversed VP model at the center. On the right, we have also the VP logs. And we can clearly see on the grades of the nickel that there is a strong anti-correlation between VP velocity and grades, nickel grades. So, but it's not linear at all. So we built, as I said, there is a free software which is called BH Tomo, available on our GitHub. This software can generate multiple simulation of the VP between wells. We can also infer some statistics, so the standard deviation. And if you look at the conventional least square inversion, it's totally fuzzy. It's too oversmoothed by, and it's not bad. It's not saying that the conventional least square doesn't work. They're designed to estimate the mean, so they cannot infer the upper and lower side of your distribution. And if you look, as I have no pointers, if you look at the third images on the board, on the screen, you have the clustered of the VP velocity versus the grade, nickel grades, and you clearly see that there are two clusters. So no conventional linear inversion can work in that case. So that's why we decided to build this kernel density estimator inversion. This allowed us to directly convert our VP simulations into grades. And also you can compute some statistics. So you have the standard deviation of the grades between the two boreholes. You can compute also the mean. So at least you have multiple realization that gives you insight on the uncertainty of your estimation. And also you have the mean value. And if you look at the model that was built by the mind, so they simply do sequential Gaussian simulation without using the geophysical data. And basically, you end up with a very large error and a model that was totally unrealistic at that time for the mind. So I think there is some interesting stuff that can be extracted from that experiment. Why don't we use seismic data, high-resolution seismic data to infer grades or lithology? So remember, I have one single question. That question was, can we predict lithology and or grades using borehole and surface geophysical data, geochemical data, and geological data? And yes, but there is a if. There is a need to new collocated data acquired at a sufficient amount, and this amount of data depends on the case study that you are working on. There is a need also to acquire more continuous and punctual data, and that those data should be smartly merged. And also, there is a need to train personnel to work with those algorithms. And unfortunately, there is, in geosciences, as far as I'm concerned, there is no lecture in machine learning or in stochastic inversion given in the university in Canada. So I'm sorry for the time.
Thanks. Yeah, thanks a lot, Erwin. I'd like to thank all the speakers who sort of took us from core scale to camp scale. And we're out of time for questions, and it's lunch, so we'll sign off here. But if anybody's got any questions for Erwin or any other speakers, they're down the front here. Thanks a lot.
Thanks, sir. That's really good.